All right, good morning everyone. Welcome back to today's set of lectures. And I'm going to start with a lecture on laser diagnostics and development tools for the PSL. So this is only about the PSL, and it's going to be a bit a more detailed session than yesterday. So I'm going to show you some of the tools we used during the development, and that includes sensors that we included into the laser box, and also the lessons we learned from the data we got from these sensors. And I'm also going to show you three devices that we used during the development and which are still in use actually. So I'm going to start with the diagnostics inside the PSL box, the pre-stabilized laser box. And then I kind of picked like three topics. One is the diagnostic breadboard, which is still, I think, one of the most powerful tools that had been developed for that laser system. And then I'm going to talk about 2 points which are more, or which came more into the game during the development of the laser system itself. And that includes the pump light diagnostics, pump light characterization, and some characterization device for the laser crystals. So I'm going to start with the diagnostics inside the laser box. Just as a reminder, yesterday I've shown this schematic. So the laser itself consists out of three components, so to say. One is the so-called front end here, this 35 watt laser, which includes a 2 watt end pro that's then amplified to a 35 watt laser beam. And then we have this high power oscillator, which is then injection locked to this system, and so we end up with a stable 200, or actually it's a bit less than 200 watt output power, but we end up with a high power output beam with a nice beam profile. So the last slide I've shown yesterday was kind of this picture from the laser table in Hanford, and I took this picture when there was still nothing else on that optical table than the laser itself. So you can see there's some spare place left here. That's for the handover to the other groups. So there's going to be a periscope here, and that brings then the laser beam out of that room. And yesterday I talked about these two parts. So that's a picture of this the front end, and that's the oscillator. And then there are a couple of other components on that table. So there's, for example, a reference cavity. For the frequency stabilization, there is a little box for the intensity stabilization. There's another box which includes a primo cleaner. And I'm going to talk about these components in one of the next lectures. So I'm going to give one lecture on laser stabilization, and that's when I introduce these components and also a bit more. And also I'm going to talk a bit about this electronic stuff here. And there's one component I'm going to talk about today, and that's this diagnostic breadboard here, which is really a little breadboard with some components on it, which I'm going to talk about later today. But let me start with the diagnostics inside the laser box. So we went through different stages when developing the laser. So there were different prototypes. So we started with a normal lab setup. We had an optical table. We put a bunch of components on it, and then we actually started doing experiments. And we went further in several steps to get really a box system which we can deliver to somebody in the US or so. One of the stages is the so-called engineering prototype. So that was at a stage where we already knew how to build that laser, how to generate this high power beam. We knew that we want to have 4 crystals. We knew how to arrange the whole thing on some sort of breadboard. But then it was time to actually design the whole thing, to decide on how we want to arrange that, which kind of sensors we need, and so on. And the engineering prototype is kind of the system where we try to learn on how to build things, how to do the cooling concept, how to machine parts, how to align that thing, and so on. And the layout of that thing is more or less as it's today. And it's the first system where we actually included really a lot of sensors, and I can tell you it really helps during the development. So we made a couple of mistakes in that first run. We were able to fix that these mistakes and find all the little clues which we haven't thought about it, just because we added as many sensors as we took. And I put a couple of dots into this scheme here, which actually show some of the sensors. So there are some outside. For example, these two I put here should represent the photodiodes inside the pump diodes. So the diodes which pump the crystals, they have an internal photodiode. But even the manufacturers said you can't just use it to monitor the power that's coming out of the diodes, because they just pick up some scattered light from the coupling into the fiber. So these photodiodes basically just tell you whether that thing is working or not, whether there's whether you have some voltage applied and whether there's some fluorescence coming out of these things or not. So what we did is we added some extra monitors for the pump diodes. I already told you yesterday that we have like 7 per crystal. And we are only interested in the overall spectrum and the overall power that's coming out of this set of 5 diodes. So we have a monitor here. I've already shown that yesterday. And that's not only a photodiode, it's also a spectrum, or actually it's a feed-through for a fiber, and that fiber can then be connected to an optical spectrum analyzer, such that we know at which, how the pump light spectrum, the optical spectrum actually looks like. And then there are a bunch of other photodiodes that are all these red dots here. So we try to monitor the backwards running power here. So it might be that the injection locking doesn't work too well. And then it might in fact be that there is some laser light oscillating in the backwards direction of that laser. And that's then picked by this photodiode. So we know that there's something not really perfect. And then we have, for example, one for the Brewster plate, which ensures the linear polarization. And if that power goes up, we would know that there's something going on with the polarization state of that thing. We monitor the power of the amplifier, which is coming in from here. So there are a couple of photodiodes. But it's not only photodiodes, we also added some temperature sensors. So we put them on the base plate and monitored on how the thing shifts thermally, whether there are some structural things going on and so on. And of course, we also wanted to monitor the temperature of the laser heads itself, because it's kind of the critical component. I mean, that's where this, well, overall, it's a kilowatt of pump hours going into that system. So of course, we wanted to know if that light heats something up. And yeah, of course, there are a bunch of power meters. One is here for the backward direction when the system is not locked. One is here in that shutter. So there are 2 shutters included in that system. One is here inside the resonator. So that's the output coupler. And then the ring is formed kind of here. And there's one shutter inside that system which actually interrupts the beam inside the oscillator. So if that shutter is closed, then there's no light actually coming, no laser light actually really coming out of that system. It's only fluorescence and pump light which has to be blocked here. And the other shutter here, that's really the shutter in front of the output. So if that system is running and we want to have it running, but we don't want to have any light outside this box, then we would just close this shutter. And it had been actually developed for the system. It's kind of hard to find a fast flipping shutter that can block like 200 watts. So this is built in a way that there's a mirror on a little solenoid inside, and that directs the power then to a power meter. So at the same time, we can actually monitor how much light is really coming out of this oscillator. And the nice thing with all these devices is that we actually built a software interface where we can actually see all the data. So it's really not that great to see on this picture. But we had a computer program where we can immediately see what's going on, like temperature-wise, water flow-wise, and so on. So the engineering prototype was the first system where we really did some long-term tests. So before that, of course, we had that system running over a weekend or so, and then we turned it off and did some experiments and did some improvements and so on. And the engineering prototype was really the first time which we turned on, and then we decided, okay, let's let it run for a couple of days at least, or in this case, it's actually a couple of 10 days, and see what this system does. If we can really build a laser that operates basically all the time, like 7 days a week, 24 hours per day. And this is kind of the power trend we get. And it looks kind of spiky here. And that's because it's still a system under development. So we turn it off, we tune things and so on. And actually, if we look at this curve and then we look at our lab books, then we can identify certain events. For example, this little gap here is when we decided, okay, let's not use a power meter as a power monitor, but let's use a photodiode. And then at that point, we sort of calibrated it to an external power meter. And so there are several events which we can identify what it is. This, for example, is where we figured out that the system actually needs a couple of days to settle down. So when we install it first, everything is aligned, we turn it on, then it actually needs a couple of days to let the components settle, let all the screws kind of settle and so on. And that's when this power went down here. So we had a little maintenance phase here, aligned everything back. And then we saw that this power drop is much less. And actually, I'm going to comment on this power drop a bit. It's sort of, I'm sorry. It's sort of related to the question Sentinel had yesterday, because we couldn't explain this power drop just by another settling of screws. I mean, we could argue like this forever, but we had the feeling that there's something else going on, and we couldn't explain it by some decay in the pump diodes or so. So we did some investigation, and we couldn't find anything fishy what's going on. So we kind of removed the most critical part of the laser system, and that's the laser crystals. And we looked at the laser crystals under a microscope, so that's these two pictures here. We actually found that there are this, I don't know if you can see that, but there are these tiny little dots on the laser crystals. So we had them perfectly cleaned, everything was assembled in a clean room. And when we looked at these crystals, we've seen these tiny little dots, and we couldn't really explain what it was until we had the clue that it might be actually condensed water or some outgassing from this Teflon O-rings, which we use to clamp the crystals actually. So that's kind of a reasonable thing, because we only found these dots here on the pump side of the laser crystals. There was nothing on the back side. So that indicates that it has to do something with the heat that is created at that side. It was kind of easy to remove these dots here. We just had to do some cleaning, so there was not really a damage. And after that cleaning, the power was kind of okay. But the consequence that we did is that we just changed this pump chamber design a bit, and also changed the size of the O-ring a bit to have a better sealing against this water here, so that these O-rings really squeeze into a little groove, and that then holds the crystal. So that was one lesson we learned, that we had to slightly modify this pump chamber design. Oh. And there's another big gap here, and that's actually really a bad thing that happened. At LIGO, it's like the chiller that is used to cool the system down is not sitting right next to the laser. People didn't want that because that chiller has moving parts. It has a little turbine, and it has some switching power supplies and so on. So people put that chiller in a different room. But that means that you need to bring the water over a distance of something like 100 meters to the laser system. And of course, we wanted to test that. So we bought a bunch of hoses, like 100 meters long. We coiled it up. We put it some distance away from the laser, just to see if the chillers we were using are capable to handle this long distance, and also how the temperature changes over the distance, if it runs through a certain room and so on. And a long story short, what happened is that we had a really big buildup of pressure, because these hoses are kind of flexible. And also the flow was a bit low, so the basically standing water inside the laser system got hot, and eventually these hoses here burst. So this is one hose at this external shutter I was talking about earlier. And the only interlock we had at that time was actually the chiller interlock. So the chiller would turn off if the tank is kind of like half empty, and then if the chiller turns off, the laser would turn off. But we didn't have any leakage detector or so inside the laser. So what happened was that all the water was actually flooding the laser box, and that's kind of the worst incident that can happen, because it's really a mess to clean all the optics, all the realignment. We were worried about rust in that laser box, and it took quite a while to fix it. So that's something like 2 weeks or so, and we were really continuously working on fixing that thing here. But the lesson we learned is that the chiller and the laser can actually handle this long distance of 100 meters. If everything is set up properly. So we kind of modified the water distribution a bit. And the main change we did was we used custom-made hoses, which are reinforced, so we don't have to worry about the pressure, and they're also temperature resistant, so we don't have to worry that the hose really blasts. And of course, we also added some interlocks for temperature and flow sensors and so on, such that the system turns off in time. So we don't have to worry with the systems which are in use right now for that. Then I want to show you some data about a temperature and humidity sensor we put into that system. It's a little, just a little sensor you can buy, but that turned out to be pretty useful. So I have 3 graphs here, all show the same time scale. This is the laser power here, so we basically turn it on with 2 little interruptions. I can't really tell why we turned it off at that time, but it was basically on all the time. And if you look at the temperature at the room where the laser was placed and inside the laser box, and you can see that there's really a strong damping. So the temperature in the laser box was always kept at around 25 degrees Celsius. So we were a bit worried that things might warm up. We were thinking about some specially shaped hood for that, such that you build up some sort of convection cooling or so for that laser. We were really worried about that, and we were really happy when we saw this graph, because it shows that not only the temperature fluctuations inside the laser room are kind of damped, we could also show that the temperature not really goes higher than like this 25 degrees or so. However, that's not true for the relative humidity in the room. That's not damped by the laser box, so it's not really tightly sealed. You can see that actually the humidity inside the laser box follows actually the humidity in the room where the laser is placed. We have a little pump light monitor. I commented on that yesterday. So this is one of the pump heads here with the pump light coming from here, and then that's imaged into the crystal through this dichroic mirror. And there's this device here in the middle which actually monitors the pump light. And yeah, I'm sorry for this little crappy descriptions here, but the light is coming from here, and then there's an AR-coated window in it, and a little fraction of that pump light of this 250 watts is actually reflected here and then sent downwards. There's another beam splitter here, and then we have a photodiode here which monitors the power, or it basically just gives you a voltage, and another fraction which comes out here, and then there is a fiber connector here, or here, it's maybe easier to see, and the fiber can be connected, and then the light can be analyzed in terms of the spectral distribution of the components. And at that time we also implemented that into the software, so that's a fraction of the user interface here, and we made it such that you can actually click on one of these laser heads here, which are schematically shown on that user interface, and that gives you another screen where you can actually see the power that's coming out here, and can also analyze the spectral distribution. So what we found for this pump light monitor at the engineering prototype was, or what at least I learned, what I didn't know before, is that you want to have a special coating for actually all the components inside that laser box. But this was the part where I really learned that lesson. So if you look again at the laser power, so that's the same graph I've shown before. So that's the relative humidity in the box. I've also shown that graph. And then you look at the pump light monitor. Then you can see that it seems that the pump power is kind of going up and down here, although the laser power is not. So that indicates that there's something wrong with that sensor, which is actually not that great. If you have a sensor to do some error monitoring and then that sensor doesn't work properly, that's not a good thing. But what we found is that this curve here strongly correlated to the humidity inside the laser box. So if you look carefully, then you can see that you have that shape here, which seems to kind of correlate it to the humidity in the box. And of course, these are the gaps where the laser was off, but you can actually follow these structures here and find that also in the humidity in the box. And what we learned was that is due to the E-beam coatings we were using. So I have a little slide for the coating. So the normal coatings that you can just buy if you buy a standard mirror or a standard substrate is called an electron beam coated coating, and I'm going to tell you in a couple of, or actually at the next slide, what that means. But the effect that really happens is that this coating consists of a microstructure which is kind of cylinders on the surface of the substrate, and then the water molecules from the air can actually slip into these little gaps between the cylinders and change the refractive index, and that changes the reflectivity of the substrate itself. So I've stolen this little graph here. So that's not directly related to the laser, but I've stolen that from some paper where people investigated that. And if you look at a certain wavelength, then you can see what happens if you have a saturated air. So there's water in the air, no water at all, and you see that the transition, that's what's on this axis here, actually changes with respect to the water that's available in that system. And that's mainly true for electron beam coated substrate. So I found this little table here. I'm not going to go through it in detail, but the main principle is for the normal coatings, you use an electron gun that is sent to the material which is going to be used as a coat for the substrate. And then the substrate is on a little disc which rotates here, and this evaporant then here settles down on the disc, and that gives you let it rotate for a certain while until you get a thickness of whatever lambda quarter or so for an AR coating, and that actually gives you the layer. And that's a standard system which causes problems, so people try to improve that a little bit, and the next step that they figured out was an ion-assisted deposition coating. And that actually means that you basically have the same principle as here, but in addition you use some sort of ion source with a high energy ion beam, which actually prepares the substrate a bit. So it acts like a little hammer, which kind of cleans and prepares the substrate such that it's easier for the evaporant to really form a dense film on that. And the coatings which we in the end use for the LIGO laser is that's all IBS coating, ion beam spattering coatings. And in that case, you actually use the ion source to kind of knock off particles from the material which is going to be settled on the substrate. And then you, instead of the electron gun, you directly use this source to put the evaporant on the substrate. So here are some pictures I got from this company which actually makes these coatings, and the scale for these three pictures is the same, and it actually shows the surface roughness, and that's an indicator for how well this coating is made. So it's also good in terms of scattering, I guess. But I think you can well imagine that a coating like this is much better than a coating like that in some sense. Okay, so I'm going to summarize some of the most important lessons we learned when we transferred from the engineering prototype, so that's the system I was talking about right now, to the reference system, which is kind of a system which is still in use. So that's a system which is identical to the observatory lasers. And some of the most important changes is, as I said, all the optics are coated with this IBS technology. We not only use this reinforced hoses, we also simplified the water system, because when we did this fix I was talking about, we really figured out that it's kind of hard to swap hoses and so on, so we simplified that a bit. We figured out from these temperature sensors which we had that we don't need a water-cooled baseplate, so that was a great relief for us, because for the engineering prototype we had this huge breadboard which we used for that laser, and we actually put some water pipes in it. So it was already hard to machine it, but we also added some water device, because we thought maybe we want to have this base plate at a stable temperature, and we need to cool it at least a little bit. But that turned out not to. So the temperature is rather stable even without the water cooling, so that saves some costs. And then we added some flow sensor for the laser heads and also for the 35-watt laser. And these are these little flow sensors for the laser heads. It's basically little turbines which can be read out electronically. And yeah, I think it's probably a good thing to have. Of course, it might cause some other trouble, like you know, this stuff here is all Teflon sealed, and you don't want to have the Teflon parts falling into the little turbine because otherwise the sensor would fail. But overall, I think it's a good thing to have that, just to be sure that there's nothing going on with the cooling again. Then we added a little fiber switch, which looks like that. So I told you at this pump light monitor, there are these little fiber outputs. And in the beginning, we always had to get an optical spectrum analyzer, roll it into the lab, attach the fiber, and then do the measurement for each of these pump heads. So that changed a bit for the reference system and also for the observatory lasers. That's a little device which can actually, it has 4 inputs for the 4 laser heads and 1 output, which then goes in a loop and goes out here. You can switch between these 2 fibers with a little piezo-driven motor that's inside this thing. So it's fully electronically controlled. And what we also added was, instead of having one of these rather expensive spectrum analyzers with all these features that we don't need, we added a little integrated spectrum analyzer. So you can actually buy that from this company here. And it's a little box with not a really great resolution, but it's anyway a cool little device if you just want to see what the pump light is basically doing. So from inside it looks like this. So the light is going in, it's sent to a grating, and then the analysis is done with an array of photodiodes which actually analyze the optical spectrum in a certain range. So we built a little software interface for that, and that enables us to just monitor the spectrum. And then we added a status screen, which sort of looks like that. So we have a bunch of things that might go on in the laser and also in the front end. And we have the status screens. Before that, we just had a little text field, which gives you a status on what's going on. And it was kind of overwriting itself. So the message would, for example, be water level low, and then the next message would be interlock triggered. So the last message that you see when you come into the lab was always like interlock triggered, but you don't know why. And that's why we came up with this little screen, which actually has this green and red boxes, also a couple of warnings. So I guess in this case the system would run because that's only warnings, like somebody opened the lid of the oscillator, somebody opened the lid of the front end, and so on. So that's things which just let you be aware of other things. So all the data are taken with a system which I don't know too much about, actually. So that's that picture I took last week, not last week, but the week before in Hanford. It's a room where all the data are collected. And the way that works is all the data are accessible via the LIGO Epic system. So Epic is an experimental physics and industrial control system. And that's basically a set of software tools, libraries, and so on, which can be used to control the system. So if you want to work with that, you open something, you grab a computer and you open something that is called an MEDM screen. So M stands for, hello, I think the battery is empty. So that's the abbreviation here. So, and it's basically a graphical user interface which had been programmed to control not only the laser but also the stabilization of that system. And the cool thing with this is that it's not only available from one computer. You log in, and then several people have access to that data from several points, can look at several data at the same point. So, but if you want to do a measurement and control something, then you probably set up all your parameters with these MEDM screens. And then the time signals are saved by some sort of frame builder in a CDS network. So that's the control room where, or the room where this CDS is actually placed. And CDS stands for Control and Data System. So that's basically the interface which actually gives access to the data. And then there's a little program like LIGO-DV. I guess one can also use something else. And that's a program where you access these sort of computers or some sort of data server, and then you can look at the trend. So that's a really great thing because you just pick the channels you want to know, like what was the humidity, what was the laser power at that time, what happened to the pump light, and then you then you download this data for a certain time period, and then you can actually compare, try to find correlations, and it's really great in debugging the system. Okay, so yeah, that's what I was going to say about the components inside the PSL. So let me go on with some other tools which are sort of not really connected to the laser. So yeah, the diagnostic breadboard is, as I said, maybe one of the more important thing, and it's a little breadboard which can do various automated measurements without having any more fancy equipment that need to be rolled in, and then somebody has to type in some numbers. It's all computer controlled, and it's a little breadboard which can do measure the relative power noise, so the power fluctuations of the system, can measure the frequency noise of that system, beam pointing. We have an option to measure the beam quality, and that whole system can be automatically aligned by some sort of feedback loop if it's already a bit pre-aligned. And here's a layout of this board here. So the beam comes in here, then it needs to be mode matched. This thing here, several photodiodes, like there are a couple of quad photodiodes. There is a photodiode which actually just picks the beam that comes in, and then there is a photodiode in reflection and transmission of this thing. And this thing here, that's a so-called pre-mode cleaner. So it's a 3-mirror cavity with a really high finesse. And that means that this system can be aligned such that only a certain mode, let's say for example the fundamental mode, can be transmitted through this cavity, so it's bouncing around here and then eventually coupled out. And all the other modes are reflected because they don't fit into the line width of that, or they don't fit the resonance of that thing. And the back mirror here, this curved mirror here, that's attached to a little piezo element, so the length of that thing can actually be shifted. So this mirror can be moved back and forward, and that changes the resonance frequency of this resonator. And that means that it can be either sort of scanned over the different eigenmodes of that thing, or it can be locked via a feedback loop such that it's really rock stable for a certain mode. So usually that's a fundamental mode. Yeah, you actually want to know how good the beam is and how much light is reflected here. So I'm gonna go a little bit through the components, the relative power noise. I think some people call it relative intensity noise, but I like this term a bit better because it's not really a pulsed system, and so actually I think that we measure the power noise. And that's a deviation from the mean value of the power. And all you need to do that is basically a fast photodiode. So you don't need this optical resonator or so. It's basically just the beam which goes to this photodiode, and then that photodiode monitors the power over a certain time. And what you expect would be something like that. So you get the power fluctuations over a certain time. You say it's like 5 minutes, and you have fluctuations of 1%. But that gives you some information, but not really the information you want. And Rana already introduced yesterday this term of the spectral density. So you basically want to have some frequency resolved spectrum of the power. And that's also something that can do kind of automatically. So there's some sort of data processing involved. And the typical curve for the free-running laser looks something like that. So you have something like 10 to the minus 3 per square root hertz at 10 hertz or so, and then it rolls off, and then there are usually some bumps somewhere in the acoustic region here. So that's a general shape that you would expect from the free-running PSL. And as you can already see, the requirements for LIGO are kind of tough, especially here at the 10 Hertz region. So that might already indicate that there needs to be something done. And I'm going to talk about the stabilization of that system and how we bring this curve down to this level here in the lecture about laser stabilization. And there are also some requirements at high frequencies that's basically measured with the same photodiodes. And that's basically the radio frequency range where, where actually the sidebands become involved. So that's 3 different curves for the 3 different lasers which are running right now. Normally, the reference system is kind of the worst because it's not in some sort of enclosure or so. It's just sitting in a lab. So it's kind of a clean environment, but it's not that quiet environment. So that's actually, I don't really know why these 2 curves here look that much different. So the frequency noise can also be measured with this device. And whenever you try to measure frequency noise, you need some sort of reference. So you need something that is more stable than the frequency fluctuations that you expect from the laser. And what people normally use is some sort of reference cavity or an atomic line or so. And then they use this line or that transmission line and compare it with the fluctuations that are coming out of the laser. And in this case, we already have a cavity, although it's not something ultra stable made of ULE or some silica glass or so. But what we use is actually the primo cleaner itself. And to keep it more stable than what the laser is doing frequency-wise, this thing has to be has really to be stabilized, and that's done again with some sort of Pound-Ruhr-Hall stabilization scheme. It's kind of similar actually to the Pound-Ruhr-Hall system. Well, actually, I would call it the same. The difference is that in this case, you don't modulate the laser beam with some sort of EOM. So in the scheme that I've shown you yesterday, you used an EOM to create sidebands. In this case, you move this back mirror here slightly with a frequency of 1 megahertz, and that actually creates sidebands inside the resonator itself here. And then you again have a photodiode which detects the reflected beam here and overlaps it with the beam that's traveling inside this cavity. And then you basically have the same scheme as yesterday. So you grab that signal. Actually, this word sum is standing here because one of the quad photodiodes is used for this purpose. You demodulate it, and then you have some PID control, which actually control the position of that mirror on a bigger scale. Pardon? What?
Why do you have to add the 1 megahertz to the PZT?
This signal? Oh, it just indicates that you need some sort of control for. So one thing you do with this mirror is you dither it with a megahertz to create the sidebands. But on a bigger scale, you need to keep it stable to the laser frequency because you really want to make sure that there's only one mode going through that. So that's why you introduce this PID controller here, or actually I think that it's more like a PI controller, and then you feed that signal back to the piezo mirror. That kind of clear. I think there's going to be a lecture about feedback loops and how to build that, but dither lock, that's what that means, that you don't use an EOM at the laser beam that creates the sidebands, but you create the sidebands inside the resonator itself by changing the resonance frequency of this thing here. And that's one of the curves that one gets out. What's shown in, so it's again a spectral density, in this case for the frequency, and the blue curve is kind of what the manufacturer of this N-Pro of that main beam gives you, and the red curve is what's coming out of the high power laser. And as you can see, all this amplification and injection locking and so on, that doesn't make it worse. So in first order, it's laying about on that curve. What you can also see is again that the requirements for LIGO are somewhere here. So especially, you can say the kilohertz region is kind of challenging because this curve goes down here, but you can also say, okay, the low frequency region is challenging because you have to stabilize that thing over something like 4 orders of magnitude or so, or maybe even more. So, but I'm going to talk about this again in that lecture on stabilization. I just wanted to show you what that system is doing and that sort of measurement works. So another thing that you can do is measuring the pointing. And pointing means basically that you measure the shift and tilt of the beam, and also the angle where it might move around. And a typical parameter that you use to characterize that is shown in this formula. So that's called the pointing parameter, and it includes basically a term for the shift in x and y. So in this case, it's only one direction, but you have another parameter for the other direction, plus another term for the angle. And the measurement is actually done with these 2 quad diodes. Quad diode is basically 4 diodes on one chip, and then you can read them out and see what the individual parts on this diode here are doing. And if you align it initially such that the beam is kind of in the middle, and then it moves up or down, then you would see that in these 2 quadrants here, the power would go up, and in these 2 quadrants, it would go down. And if the overall sum power of the whole thing somehow changes, then you would know that there's something else going on, like power fluctuations or so on. So why do you need 2 photodiodes? 2 of these quad photodiodes to make this little drawing. And you need that because otherwise you couldn't distinguish between shift and tilt. That's if you would have only these 2 upper photodiodes here. So that's the situation where the beam is just shifted. That's the situation where the beam is tilted. Then it's really hard to tell, well, what's going on, right? In both cases, this reflected yellow beam here is moved to the upper 2 quadrants, and you can't distinguish that. But if you have another photodiode, then you would be able to tell what's going on. So that's basically what you want to do. And in principle, you can just use these 2 quad photodiodes and then look at this and tell what's going on. But to do so, you would need a really, really stable setup. So you would really need to make sure that the position of these photodiodes doesn't change. And yeah, the thing is rock stable. So a much more precise measurement is what's called differential wavefront sensing. And the way it works is like the interference pattern. So you get this red beam, which is which is actually coming out of the cavity. So the cavity is locked, and you would assume that that's your reference. So yeah, that's actually the beam you really use as a reference. And then you look at the reflected beam, and you overlap it as in this Pound-Ruhr-Hall scheme with the transmitted beam, and you can find then the phase shift between these 2 should be pi. However, maybe I make a little drawing here. If you have a slightly tilted beam, then you would add some non-regular interference pattern. So if you have your photodiode here, and then your reference beam is coming in like that, let's say it hits in the middle, and your wavefront sort of looks like that. And then you have another beam, which is slightly tilted. So that's what you try to measure here. Let's say it looks like that, and it's tilted with an angle, let's say alpha. Then the wavefront would look like that. Oh, it's a kind of a bad drawing here. And normally the phase shift over the whole beam should be something like pi. But if you now look at, for example, this front here, then you would see that for the upper 2 quadrants here, you add or subtract something, and here this arrow goes in the other way. So you end up with something like pi plus some phase shift phi. You would end up with pi minus a phase shift phi. and phi is somehow proportional to that angle alpha that you have. All you have to do is now you subtract this region from that region, so you end up with something. Yeah, so you end up with a signal where 2 phi is proportional to alpha, and that gives you some information on the tilt of the laser beam actually. So that's how this differential wavefront sensing works. Oh, maybe I turn that off again. So here's the signal that you're getting out. It's again this spectral density over the frequency, and you end up with four curves for x and y shift and for tip and tilt. So it's 4 curves, and you can again see that they are slightly above the requirement. So this black curve here is the requirement, and again I'm going to tell you how that can be fixed in this lecture on the stabilization. But in this case, it's not too bad, I would say. So it's quite close to the requirements, and there's anyway not too much you can do against it. I mean, you can try to build things a bit more stable and so on, but we never really figured out how to reduce the pointing engineering-wise, really. And then one really cool feature of this optical resonator here is, as I said, that you can analyze the laser beam for different modes. So what you do is you don't lock this thing in this case, so you don't use this Pound-Ruhr-Hall locking scheme or something. You just scan this mirror here. And that actually changes the resonator length, and that changes the resonance frequency of that thing. And that means that several components of the laser beam can pass through, and other components here are reflected. So this is the calibration curve for that, and it's taken by moving this mirror here and then looking at the highest peak, which is expected to be the fundamental mode peak. And then you actually look at the voltage difference for that, and that gives you these two curves. And as you can see, it's not as nice and linear as you would like to have it. They are slightly curved. So I think what the software for this analysis then does is you need to have some sort of calibration for this piezo mirror here. So you put these curves in, and then you say, okay, I scan over at least one free spectral range, so the two high peaks, and then you analyze what's going on in between these two high peaks and have a look at the mode pattern. And that's how it looks like. So these are the two fundamental modes, which are normalized to a free spectral range. And then you can see all these peaks in between it. So there are 3 curves for the 3 different lasers again. In this case, the reference system, which is still in Hanover, is the best. And my suspicion is that the only reason for that is that it's sitting there and people are doing these mode scans all the time. They try to improve things. So it's simply that the mode matching is probably the best for that system. I believe that the systems are more or less the same free running. So yeah, that's how it looks like. Okay, how much time do I have? So 10. Okay, so let me talk a bit about other things. So I picked these 2 things because I think that they are sort of the most important features that we have. Of course, we're doing a lot of diagnostics and incoming inspection. We built a lot of cool tools. We had a couple of ideas, but these might be the most the things which brought us really forward. And as a pump light characterization, of course, if you want to see how the pump distribution in the laser crystal is, and you have a certain pump light source, the first thing you want to do is you want to do some simulations. And the tool I normally use for that is this commercial software, which again, there's not much to see, but it looks kind of crappy to work with it, but it's a really good software. It's also kind of expensive, ZMAX. And what you can do is you put in all the parameters you know about your pump light source. You put in all the curvatures and materials and so on about your optical components. You put in all the parameters you know about your laser crystal here. And then you pick a certain amount of rays, and then it does an analysis in a way that it's not only geometrical optics, it's really doing wave optics, it's taking in, scattering into account, and also reflections, of course, and so on. And then it gives you the option to put detectors, virtual detectors somewhere, and just analyze what's going on there. So you would, for example, see if you come up with a pump optics or a set of lenses where actually a part of the light here doesn't hit the crystal, so it's going the other way, or if the coating is the coating on the backside of the crystal is only what do I know, 95% reflective or so, and then there's light leaking out, so you could analyze how much it is. However, you need to know what the parameters of your pump light source are, so the simulation only gives you a rough idea. It never really fits perfectly, and that's why we actually, of course, also doing some measurements. And now you can come and say, okay, let's do the measurement in a way like we built this pump optics that you just described, and then we put some sort of camera or rotating slit or whatever somewhere next to the position where the crystal is, and then we analyze the light. That won't give you a real picture on what's really going inside the crystal, because you won't have the crystal parameters. And I can tell you it really matters whether there's an undoped end cap, the beam propagating inside the crystal. And that's why we came up with this sort of test crystal here. And that's a little crystal with a relatively large undoped region, so that's just yak. And then there's a highly doped thin slice here with a thickness of about a millimeter right in front of it, or actually on the back side of it. What we do is we shine the pump light into this crystal, and then that pump light is absorbed, of course. There's not really lasing involved because the laser mirrors are missing, so there are no laser mirrors around, but there will occur some fluorescence, and this fluorescence is emitted isotropically, so you basically, yeah, it's basically going in all directions. And but anyway, the fluorescence is created where the most pump light is. So we assume that the pump light is kind of proportional to the fluorescence which is created in first order. But what we want to do is we want to only look at fluorescence rays which are kind of coming paraxial out of this thing. So we built this telecentric telescope here. And what that does is, with this pinhole in the middle here, it selects the beams which are just parallel to the, basically to the surface of the optical table or whatever is around here. So you have this light coming out in all directions here. You put a 2F imaging optics in between, and then you have this pinhole, which is kind of the key component, which ensures that you block all the light which is not coming paraxial out of the crystal, and then you image that on the other side to a CCD camera. And the pictures that you get out they look kind of that. So that's the picture, and of course it's kind of an integrated thing, because this highly doped slide that I was talking about earlier, that has of course a certain, you read the profile in a plane, it gives you the profile integrated over a millimeter or so. But at least you get a better idea on how the pump light propagates along a certain distance. However, that's still not really what you want to know. What you want to know is, how does the pump light propagate inside a laser crystal? I mean, the laser crystal has a much smaller diameter than this test crystal which we have here, and you do not really want to know how the light propagates if there's no optical medium involved. What you want to know is, how does the pump light look inside the crystal? So instead of this little test device that we had, you could also just put a laser crystal in here, pump it, make sure that there's no laser emission involved. So you don't want to have some sort of resonator here. You just put the light into that crystal, fluorescence occurs in it, but this time you are also taking into account that there might be some reflections at the barrel of this crystal for the pump light, and that actually gives you an information on how the overall pump spot integrated over the length of the crystal looks like, and that's what you really want to put into your simulations for the laser and also for the analysis of the pump light itself. And I brought a couple of pictures on how it might look like. So there are 3 situations. In all situations, so that's sort of a CMAX simulation here, and that's a measurement. In all situations, the pump optics is the same. So the real spot size of the pump light is always the same. But you shift the crystal around. And what you then see is that this integrated pump spot that I was talking about looks different depending on where you put the spot of the pump light. So if you put it, for example, into this undoped end cap here, then the light will be, when the light is then absorbed, then you're already where the first absorption, the first reflection at the barrel is. And that means that you get a rather big pump spot here. Whereas if you put the spot of the pump light somewhere, then that means that you have a high absorption in this region, and then of course a lot of the pump light is gone, so this bigger effects here don't play such a big role, so the spot that you end up with is kind of a bit smaller. In any case, what you normally see if you have these reflections at the barrow is this little wings here. So if you look at the profile, then you normally get some little dip here, which just comes from the reflections of the barrel. And of course, the main thing here is kind of similar to the main pump, to the real, not integrated pump spot. So if you do this measurement for different crystals, then you would see that you can actually use the crystal, then you can change the position of the crystal, as I've shown you before, and then you can analyze how does the spot diameter look like. And of course, the spot diameter depends in this case on the absorption, on the pump light spectrum, and so on. And yeah, I mean the key point on these slides here is that it depends on the doping concentration of the crystals, because if you have a high doping, then that means that a lot of pump light is actually absorbed in the first few millimeters of that crystal, and there's not that much left in the end, so that means that you normally get a smaller pump spot than in the other case. So if you analyze 2 of these crystals here, and then you look at this integrated spot diameter with respect to the distance between the pump optics and the crystal, and you end up with different curves, then that indicates that there is something going on with the doping concentration in these 2 crystals, so they are different. And the consequence of that is kind of shown in this graph. So that would, if you have a different doping concentration from the different diameters here, then that would indicate that, or that would lead to a different thermal lens, and that would actually change the stability range of the resonator. That's kind of the thing I was talking about yesterday. So it would be really bad if you need a spare crystal, you go to a drawer, you grab a random crystal from some manufacturer, and they're all different. So you would have to start all over with your alignment. And that's what's actually coming out of this measurement, is that you really want to know how the crystals look like, and you want to do some sort of incoming inspection. So we decided to do that, and I think we have 2 really cool methods to do that. One is you use a Titan sapphire laser, and that actually emits light around the pump wavelength of the, or where you actually pump the crystals in the laser setup. You send that to the crystal, so that would create some fluorescence, and then you image that fluorescence with some kind of imaging optics. I think in this case I used just the optics of my photo camera and put that picture on a CCD. And if you then scan over the wavelength, so a Titan sapphire laser has the big advantage that you can tune it over a big wavelength range, then you would see that depending on the wavelength where you are, the light is absorbed in different fractions of the crystal. So, for example, in this situation where you have a high peak here, that would indicate that you basically really meet the absorption spectrum of that laser material, because the light is immediately absorbed somewhere here. And in this situation, you would say, okay, the light is basically passing through, so I'm probably somewhere far away from the main absorption peak of neodymium. However, now you can grab one of these pictures, preferred one in a region where you do have some absorption. You analyze this picture in terms of, like, you take a cut through it and then you plot the data here. And what you can then do is you use just Lambert-Beer's law, so you would know that it's an exponential decay here, or actually it's this formula. And this decay depends on the length of the crystal and on the absorption coefficient. And then in this case you get a second term because the crystals are coated for a double pass, so there's an HR coating on that side, and that means that there's also some light going back, and then you have to add this term here to this exponential curve. But you're basically able to fit it, and if you know the length of the crystal, then you would get some information on the absorption of that material. And if you now compare the absorption with an absorption of a known spectrum, so if you know, for example, the absorption for a crystal which is doped with 1% neodymium, then you can compare these data and tell something about the absorption of that thing, and that's exactly what's shown here. So that's the absorption spectrum of a neodymium crystal. These are the data points I got with exactly that measurement. And as you can see, there's not much going on in this region here, so that's pretty bad data. One basically couldn't get anything out. But here at this point where you do have some absorption, so we normally use this peak here for pumping that laser crystals, you got all these little dots, and then you can tell how big the doping concentration is. So this scale here is with regard to the black curve, and this red dots here are kind of scaled because I wanted to show that the shape of these data points kind of follows this curve here. But you can analyze that, or actually that's done for this marked region here, so I decided not to use these data points. And what you get then is some information on the doping concentration. It's not really great data, so there's a big error involved, but you kind of got an idea. So we were aiming for this doping concentration here. That's what we want for LIGO, and it turned out that the crystal I analyzed here was slightly higher doped. However, you don't get any information on the longitudinal doping concentration, and that's why we came up with another device. And that works in a way that you have some sort of white light source on one end, then you image that white light source to a crystal, and then you just look at the absorption at a certain wavelength. So you use a certain wavelength for your analysis. You kind of get two reference points. One is for zero absorption somewhere in the undoped end cap. The other one is this spectrum that you know already. Then you want to grab some information on how your light source behaves. And then you analyze this little fraction of the crystal here with this method. And actually, we built a pretty cool stage, I think, where you have a motorized DC stage that automatically moves that crystal forward and backward. And then you read out the spectrum analyzer also automatically. Actually, we had a student that wrote a really nice little MATLAB script to control all these things and so on. And then you end up with curves like that. So what's shown here is a position along the crystal axis, and then the doping concentration, which is calculated from the absorption. And I have two examples. One is a crystal which consists of sections of differently doped pieces. And in red, it's shown what we actually ordered from the manufacturer, and the red dots are the points we measured with this method. And it turns out that in this case, it worked really well, actually. In this case, however, it didn't work that well. We ordered a crystal which should have a doping concentration of 0.7%, so that would be here. And it's not only that this crystal is not really what we ordered, it has a higher doping concentration. It's also that you have this sort of gradient along the crystal axis. And that's something that you usually observe in crystals, even in the LIGO crystals. And if we have time, then I'm going to talk about that in the next lecture on thermo-optical effects. But that's really a problem, and it's getting worse especially if you have low-doped crystals, percentage-wise. Okay, so let me summarize what I tried to tell you. I've shown you that we have a system with a lot of sensors. So in the meanwhile, we got rid of some of these, especially these temperature sensors, because they didn't actually really show anything, or we know what's going on there. I've shown you that we have a lot of channels to analyze, and I'm not really sure about these numbers, but I think for advanced LIGO, we have something like 300 channels overall, and some of them are fast, some of them are not so fast, but for some channels, you really need a high data density. I've shown you the diagnostic breadboard as a, oh, there's a typo here, as an analysis tool, and I've shown you how we characterize the pump light as well as the crystal material. And yeah, that's what I have for today. Questions? Vanessa?
Are there any beam quality requirements for LIGO?
I think the beam quality requirement is more like the kind of okay, you want to have a TM00 beam with a power content of something like 165 watts at a certain position, let's say behind the primo cleaner or so. And we know that we never have like 100%, or well, actually it's not that bad. We have more than 99% in the TM00, but there are some losses. And yeah, I mean, if we see that the losses are somewhere in the 20% region, then we might want to build a 240 watt laser or so. So that's kind of more like how it goes.
You also mentioned about...
So that's one requirement, and the other requirement is that at a certain position you don't want to have too much in higher order modes, because of course this light, which is not useful for the interferometer, needs to be blocked somehow.
When you mentioned about the higher order mode content, you mentioned it in percentage. How is that measured?
The higher order mode content?
Yes.
We use this primo cleaner scan that I've shown with these two high peaks and all these little peaks in the middle. And what you basically do is you sum up the power in the peaks between the free spectral range. Of course, it's not really perfect because you only have a certain resolution and so on. But it gives you a really, really good idea actually on what it is. So instead of saying something like, okay, we have an M² factor or a beam quality factor of 1.2 or so, we say we have something like 98% in the TM0, because even 95% would, if you do a standard beam scan, that would give you a beam quality of factor of 1. So it's not really something useful in this case.
Thank you.
Other questions?
As you told that you have displaced your chiller from near laser to some faraway location.
Yeah.
Are there any major changes in the chiller design for this?
Not really. It's not exactly a standard chiller, but the components inside are kind of standard. So it's basically, actually it's two chillers, one for the diodes and one for the laser itself, and the ones for the diodes are not that critical because the diodes are also kind of like 100 meters away. For the laser itself, it's basically a standard chiller.
Okay, so at least the pump must have been changed to take care of such a long distance piping and all.
You can buy something like that. So you calculate the requirements, so you try to calculate the pressure drop and so on, and then you order a chiller which actually can handle that.
So that is what have been done in your lab?
Yeah, actually it happened in Hanover. So the trick, so for LIGO, I have some pictures of that in my very last lecture, but for LIGO, there's a system of tubes running from a so-called chiller room to the PSL enclosure. And we didn't have that. We didn't even had this 100-meter long lab somewhere in Hanover. So what we did is we bought a 200-meter long hose, cut it in half, like one part for the way to the laser, one part for the way back. And then we tried to kind of simulate a worst case scenario by putting the chiller somewhere in a tower. So there was a tower at AEI and we put it on the, I don't know, second floor or so, and the laser was somewhere in the basement. And then we wanted to see what happens. And the first thing we have seen was like the coiled up hose, which was laying there, was kind of expanding. So that material is sort of flexible. And that whole thing basically started growing. So that was the first thing we were seeing, and that was already the point where we were a bit worried. But then we have seen that there's also some water coming back through the hose, and we thought, well, okay, let's see what happens. And yeah, that's how we basically did that test. So what we did in Hanover was kind of the worst case scenario.
Okay.
Yeah.
Thank you.